At Yellowstone National Park, scientists are not looking at a volcano that is simply at rest. What they are observing instead is a system that continues to shift, release, and regulate itself in ways far more active than a surface view of geysers and hot springs might suggest. So what does it really mean when researchers describe something beneath Yellowstone as breathing? Why would a magma reservoir deep underground matter if there are no clear signs of an imminent eruption above? And how can such subtle movement even be detected through kilometers of solid rock? Recent seismic imaging has revealed a sharply defined cap located about 3.8 kilometers, or roughly 2.4 miles, beneath the northeastern section of the caldera, and evidence suggests this layer allows gases to rise gradually, preventing pressure from accumulating to dangerous levels. The new picture comes from controlled source seismic imaging, a method that uses artificial vibrations instead of waiting for natural earthquakes to do the work. In Yellowstone, researchers used a 53,000-pound vibro-sized truck, which is about 24 metric tons, to send signals into the subsurface during nighttime fieldwork. Those signals were then recorded by permanent stations and hundreds of temporary seismometers placed around the caldera. The goal was direct and practical: sharpen the view of the top of the magma reservoir and determine whether the transition from solid crust to magma is gradual or abrupt. The answer was the opposite of blurry. The reservoir's upper boundary emerged as a very sharp interface, less than about 100 meters thick, with reflections indicating a mixture of supercritical fluid, magma, and solid crystals, rather than a simple two-layer boundary. That sharpness matters because Yellowstone is not underlain by a single, simple chamber. The U.S. Geological Survey describes two main magma bodies beneath the park: a shallower rhyolite reservoir stretching from about 5 to 17 kilometers, or about 3 to 10 miles, beneath the surface, and a deeper basalt reservoir extending from about 20 to 50 kilometers, or about 12 to 30 miles, down. The shallow chamber is mostly solid, with only about 5 to 15% melt, while the deeper reservoir contains only about 2% melt. In other words, the system is not a giant underground lake of molten rock. It is a complex, crystal-rich structure with limited melt and a lot of solid material, which is one reason scientists have been so careful about how they describe eruption risk. The part that has drawn the most attention is the idea that this cap behaves like a lid, but not a sealed one. The Nature study says the magma reservoir top is marked by a sharp reflective cap at about 3.8 kilometers depth, and that the cap contains a mixture of supercritical fluid and magma. The research also argues that the bubble volume fraction at the top of the reservoir is lower than what is usually seen before rhyolitic eruptions, while the hydrothermal system above it is already carrying high fluxes of magmatic volatiles to the surface. Put plainly, gas appears to be moving out through cracks and channels rather than pooling into a dangerous overpressure event. That is the core of the breathing idea. Not dramatic bursts from the chamber, but steady release through a porous, crystal-rich upper zone. The USGS analysis adds another layer. In its summary of the work, the agency says the new controlled source data show a very sharp transition at the reservoir top, and that a two-part mixture of only magma and solid crystals does not fit the reflections nearly as well as a three-part mixture that includes supercritical fluid bubbles. The same USGS explanation notes that the best fit model is a crystal-rich reservoir with less than 30% porosity, a structure in which channelized bubble escape can help prevent instability. That matters because Yellowstone's surface features already hint at a subsurface plumbing system moving heat and gas upward. The park's geysers, fumaroles, and steaming basins are not separate from the magma system. They are part of the release pathway. The new imaging also helps explain why the volcano's upper crust can stay active for so long without crossing into eruption. The hot zone beneath Yellowstone is not only about melt, it is also about volatile behavior, fluid movement, and the way crystals and pore spaces shape how gases travel. According to the Nature paper, the observations are consistent with a reservoir that still receives volatile enriched melt from deeper in the system, but that currently releases bubbles efficiently into the hydrothermal network above. That is an important distinction. A reservoir can be active without being primed for an explosive event. It can remain dynamic, with pressure redistributed by fluid migration, even while the surface continues to show only the familiar signs of Yellowstone's geothermal personality. That wider context is important because Yellowstone has long been watched for deformation, and not every change points toward disaster. The National Park Service says the caldera has gone through repeated periods of uplift and subsidence, including a rise of about 27 centimeters, or 10.6 inches, from 2004 to 2010 at the White Lake GPS station. The same page notes that such episodes can last for thousands of years without erupting. The USGS similarly explains that Yellowstone has experienced major deformation and seismic changes in the past, including a notable uplift episode in the Norris area, followed by subsidence after a magnitude 4.8 earthquake in 2014. The lesson from those records is not that change equals eruption, but that Yellowstone is a highly active volcanic and hydrothermal system whose surface can shift for reasons that are still being worked out. That is why the wording breathing fits the new findings so well. It suggests a reservoir that is not locked down, but also not inflating toward failure. The cap appears to be doing what a venting system does best, allowing gas to move out gradually instead of building pressure in one place. The result is a volcano that remains alive beneath the park, but whose current structure and gas behavior do not match the conditions scientists usually associate with an eruption-ready reservoir. The most striking thing about the discovery is not that Yellowstone is active, it is that its activity may be part of what keeps the system from becoming more dangerous. Seen in that light, the new study does not rewrite Yellowstone as a volcano on the edge of eruption. It refines how scientists understand its internal plumbing. The upper part of the reservoir is not a vague zone of uncertainty anymore. It now appears as a distinct cap, sharply defined and shallow enough to matter, but still made of a mixture that allows bubbles and fluids to migrate. The study's estimate of about 3.8 kilometers, or about 2.4 miles, to the top of the reservoir gives a firmer reference point than earlier broader estimates, which had ranged from roughly 3 to 9 kilometers, or about 2 to 5.5 miles, for the top of the magma storage region. That kind of narrowing is valuable because the exact depth and structure of the cap influence how pressure, heat, and volatile rich fluids move through the system. Just as important, the new seismic reflections suggest that the top of the reservoir is not just a single smooth surface. The data point to a layered, chemically and physically active transition zone where supercritical fluids and magma coexist in the pore space between crystals. That is a more complicated setting than a simple molten chamber, and it helps explain why Yellowstone can keep feeding its hydrothermal features without showing the signs of runaway failure. The surface expression of that system is easy to see in the park: geysers, hot springs, steaming ground, and shifting hydrothermal areas that have long reminded observers that Yellowstone's heat source is still working. The subsurface explanation now looks more specific. The system may be behaving like a natural pressure release network, where gas escapes through connected pathways and the cap remains strong enough to hold the reservoir together. The role of the hydrothermal system is central. The Nature paper says measurements of the hydrothermal system show high fluxes of magmatic volatiles reaching the surface, and the USGS explanation notes that the best interpretation is efficient bubble ascent into that hydrothermal network. This is where Yellowstone becomes more than a magma problem. It is a coupled magma and water system, with heat from depth driving water circulation, gas transport, and the spectacular surface features that made the park famous. In that setting, the steam and boiling water are not random decoration. They are part of the way the whole system breathes. The cap does not have to be perfect. It only has to be porous enough to vent gas while still retaining enough strength to keep the reservoir stable. That interpretation also helps place the findings against Yellowstone's long-term eruption record. The U.S. Geological Survey says Yellowstone is not overdue for an eruption and that volcanoes do not follow predictable schedules. The agency's frequently asked questions also states that the annual probability of another caldera forming eruption is about 1 in 730,000, or 0.00014%, based on the average of the major past eruptions. Those numbers are not a forecast, and the USGS is careful about that point, but they do show how remote a large caldera-forming event is in any given year. The new breathing cap fits that broader caution. Active does not mean imminent, and a dynamic reservoir does not automatically mean a catastrophic one. Even so, Yellowstone remains a place where small changes matter. The USGS has documented how uplift and seismicity can rise together, and how the ground can later subside without an eruption following. In one noted example, uplift in the Norris Geyser Basin area exceeded 15 centimeters per year, or about 6 inches per year, before the deformation pattern reversed after a magnitude 4.8 earthquake. The agency has also noted that a similar area began uplifting again in July 2025, with seismicity increasing in the same general region. That does not mean the system is racing toward an eruption. It does mean the park is still full of moving parts, and scientists continue to watch those movements because they reveal how fluids and melt migrate beneath the surface. The newest study strengthens that monitoring effort by giving researchers a better target. If the top of the reservoir is sharply defined at about 3.8 kilometers, then future imaging, deformation analysis, and geochemical work can be tied to a more precise depth horizon. That matters for understanding how hot fluids rise, where bubbles accumulate, and how stress changes across the upper crust. It also matters for the public, because Yellowstone often gets reduced to a single misleading question about when it will erupt. The more useful question is how the volcano works right now. The answer, based on the latest seismic evidence, is that Yellowstone's magma system is still alive, still venting, and still shaped by a cap that appears to be releasing pressure rather than storing it for a catastrophic release. That clearer framework matters because it changes how the entire Yellowstone system is read. The cap is no longer just a vague boundary somewhere above a magma reservoir. It is the point where melt, crystals, and volatiles appear to meet in a way that lets the system shed pressure without losing its strength. That is a delicate balance. If the cap were too tight, gases could accumulate. If it were too open, the reservoir would not retain enough structure to behave the way it does now. The new seismic picture suggests Yellowstone sits in that middle ground, with a top layer that is compact enough to hold together and permeable enough to breathe. This also helps explain why the park's famous surface features are so important to the science. Yellowstone's geysers, hot springs, and steaming vents are not separate from the deeper volcanic system. They are part of the outlet. The hydrothermal network above the magma reservoir carries heat and magmatic gases upward, and the latest study says that transport is happening at high fluxes. That means the visible activity at the surface is not just scenic. It is one of the main ways the system releases what it receives from depth. In that sense, the park's surface activity is a direct expression of what the subsurface is doing, not a distraction from it. The practical meaning of that is easy to miss. A volcano does not need to look calm or empty to avoid an eruption, and it does not need to look wild to be dangerous. Yellowstone is a reminder that volcanic behavior can be steady, efficient, and highly active without being immediately threatening. The USGS describes the magma bodies beneath the park as mostly crystalline, with limited melt in both the shallow and deep reservoirs. That matters because a magma system with low melt fractions behaves differently from one full of mobile lava. It can store heat, move gases, and respond to pressure changes while still remaining far from the kind of melt-rich state that usually precedes major explosive behavior. The same distinction helps make sense of Yellowstone's long record of ground deformation. The park has experienced periods of uplift and subsidence that do not neatly match eruption timelines. The National Park Service notes that Yellowstone has gone through repeated deformation episodes, including measurable uplift over years at White Lake, while the USGS has documented other uplift and subsidence cycles in the caldera and nearby geyser basins. Those changes show movement, but movement alone is not the same as a pending eruption. The new cap image gives those shifts a better physical context. They may reflect the way pressure is redistributed through a reservoir that is still venting and adjusting rather than accumulating toward failure. There is also an important temperature and chemistry story behind the scenes. Yellowstone's system is powered by heat rising from depth, but the way that heat is stored and transferred depends on the arrangement of crystals, melt, and gas. The new study's sharp reflector at about 3.8 kilometers depth suggests the reservoir top is not a diffuse transition zone, but a distinct boundary where conditions change quickly. In that zone, fluids may exist in a supercritical state, meaning they do not behave simply as either gas or liquid. That makes the upper reservoir more dynamic, but also more stable in one specific sense. The gases can move through connected spaces rather than collect into one large pressurized pocket. That point is central to the breathing description. Breathing is not a perfect metaphor, but it captures a rhythm of exchange. Material rises from deeper reservoirs. Volatiles separate from melt. Some of those gases move into the hydrothermal system, some heat water circulating above. Some contribute to the park's constant steaming and bubbling. The system is not dormant, yet it is not locked into a runaway state either. It is exchanging matter and energy across several levels of the crust, and the new seismic data help show where that exchange becomes especially efficient. That makes the top of the reservoir one of the most useful places to focus future monitoring. If scientists can track how the cap changes over time, they may gain a better sense of how Yellowstone releases gas, how pressure evolves, and how the hydrothermal system responds. The value of the new result is not only that it identifies a depth, it also identifies a structure. A sharp, reflective cap provides a reference point for seismic work, gas studies, and deformation measurements. It gives future observations something more precise to compare against, which is especially important in a system as complex as Yellowstone, where multiple processes can produce similar surface signals. At the same time, this sharper understanding should not be confused with a prediction of eruption. The USGS has repeatedly emphasized that Yellowstone is not overdue for one and that volcanic eruptions are not scheduled on a human timetable. The agency's probability estimate for a caldera forming eruption remains extremely low in any given year. And the broader geological record shows that the park's magma system has persisted through long periods of change without erupting catastrophically. The new study does not alter that basic picture. It adds detail to the internal plumbing, showing how the system currently behaves, and that behavior is more consistent with controlled gas escape than with dangerous pressure accumulation. That is why this finding matters even outside the volcano science world. Yellowstone has always been a place where the surface draws attention, but the real story is underneath it. The geysers, the heat, the changing ground, and the restless seismicity all point back to a deeper structure that is active but not necessarily unstable. The latest evidence suggests the reservoir is not sealed off from the rest of the crust. It interacts with the hydrothermal system, vents volatiles, and holds together through a balance of melt, crystals, and fluid. That balance may be what has allowed Yellowstone to remain one of the most closely watched volcanic systems on Earth without tipping into eruption. Seen that way, the discovery is less about alarm and more about precision. Yellowstone is still hot, still moving, and still releasing gases. The difference now is that scientists can see a little more clearly how the system does that work. The cap at a few kilometers depth, the volatile rich reservoir beneath it, and the hydrothermal outlets above it all appear to be linked in a way that lets the volcano vent steadily rather than build toward a sudden release. That is the meaning of the breathing beneath Yellowstone, not a warning siren, but an active volcanic system keeping itself in motion through a controlled exchange between depth and surface.